This video is on solid revolution and then using the shell method to find the volume of the solid revolution. And here I have two graphs, the graph of sine of x plus 1, which is this one, and then the graph of 0.4x minus 2 squared, which is this one. And then to find the points of intersection right here and right here, we're going to use what's called the Newton's method. And so if we revolve this region right here around the line x equal to 4, then this is what the solid revolution will look like. And so here's the yellow region again, and then now we're going to revolve it about this line, and then this is the solid revolution. And so the first thing that we need to do is find the points of intersection right here and right here. And to find the points of intersection, we're going to set the two functions here equal to each other. So we get sine of x plus 1 equal to 0.4x minus 2 squared. And so let the function h of x be sine of x plus 1, and then move everything here to the left side. Then we get minus 0.4x minus 2 squared equal to 0. And the solutions of this equation right here, to find the solutions, we're going to use what's called Newton's method. And so to use Newton's method, we're going to need the derivative. So the derivative sine of x is cosine of x, and then the derivative for 0.4x minus 2 squared is negative 0.4. And then if we expand this out, this is x squared minus 4x plus 4. So the derivative would be 2x minus 4. And now let's look at the graph of h of x here, so we can see approximately where the solutions or the x-intercepts will be. And here's the graph of h of x. So this is the graph for sine of x plus 1 minus 0.4x minus 2 squared. And so we can see that the x-intercepts looks like it's about 0.2 and 3.2 by just looking at it, or 0.1. And so to get this x-intercept right here, we can use Newton's method, and then to get this x-intercept here, also Newton's method. The formula for Newton's method is x sub n plus 1 equal to x sub n minus h of x sub n dividing by the derivative of h of x sub n. And so here we're going to look like this is about 0.2, so we'll use an initial guess of 0.1, and then we'll calculate x sub 2 using this formula right here, and then we'll get the 0.240559, and then continue on to the next iteration. Then x sub 3 will be 0.40562. And then I did this for 8 iterations, and x sub 8 is 0.24056. And so that tells us that the x-intercept right here is going to be 0.240562. And then if we go back to this function right here, when x is 0.240562, the corresponding y is 1.238248. And similarly, to find this x-intercept here, and then we'll use the initial guess of 3, and then using the Newton's method formula right here, and then x sub 2 will be 3.414035, and then x sub 3 will be 3.381144. And then after 8 iterations, we'll get 3.3810. And here's an illustration of Newton's method. And so here's the h of x right here. And then this is the derivative. And then the initial guess is 3, since we want this x-intercept right here. And so I'm going to do 8 iterations. And so at the end of the 8th iteration, it tells us that the x, this point right here, is going to be about, the x-intercept right here is about 3.381004. And so what we have just found is that this point right here, which is the point of intersection right here between the two graphs, x is 0.2405, and then for this point right here, the x is 3.381. And now what I'm going to do is I'm going to divide the solid of revolution into 8 cylindrical shells, and then find the volume of each shell. And that'll give us an approximation for the volume of the solid of revolution. And so here's shell number 1. And so those are the 8 shells. And now I'm going to calculate the volume of each shell. So here's shell number 1. And altogether, the volumes of the 8 shells is 56.0423. And therefore, the volume of the solid of revolution that we want will be approximately 56.0423. And again, this is only an approximation. And if we want the exact answer, then we need to divide the solid of revolution into an infinite number of shells. And here's what the one of the shells looks like. So let's call this the ith shell. And so let's figure out what the volume of this ith shell is. The distance from here, from the center of the shell to here, that's called the inner radius. And then the distance from here to here is going to be the outer radius. And then right in the middle. And so this point right here on the x-axis, let's call it x sub I star. And so the distance from here to the middle of the shell is going to be the average radius of the shell. And the distance from here to here will be x sub I star, and therefore the average radius of the ith shell will be 4 minus x sub I star, since the axis of revolution is the line x equal to 4. So that's the average radius for this ith shell. And then to get the height for this ith shell, then we're going to need the graph of g of x, and we're going to need the graph of f of x. This right here, this is x sub I star. And so the distance from the x-axis to the graph of g of x is going to be g of x sub I star. The distance from x sub I from the x-axis to the graph of f of x is going to be f of x sub I star. And therefore the height of this ith shell will be f of x sub I star minus g of x sub I star. The volume of a cylindrical shell is 2 pi times the average radius times the height times the thickness. In this case, the average radius is 4 minus x sub I star. And then the height is going to be f of x sub I star minus g of x sub I star. But f of x is sine of x plus 1. So we get sine of x sub I star plus 1. And then g of x sub I star be 0.4 times x sub I star minus 2 squared. And then the for all the shells, let's make all of the thickness the same. So let all the shells have the same thickness. And let's call it delta x. And so the volume of the ith, so the thickness of this shell right here will be delta x. So the volume of the ith shell is going to be 2 pi times the average radius times the height times the thickness. And then the sum of the volumes of an infinite number of shells is going to be the integral from 0.405 to 3.3809. Recall that the points of intersection right here, this point right here, the x is 0.240562. And then this point, the point that's right here, is the x is 3.381. And so that's why the integral will go from 0.0240562 to 3.3809. And then this integral right here, if we expand this out, we're going to get the term x times sine of x. And to find the integral, the antiderivative of x sine of x, that's going to involve integration by parts. And that's going to take at least 5-10 minutes. And so let's just go ahead and use numerical integration like trapezoid's rule. And then we'll get 55.62937. So this is the volume of the solid of revolution when we divide the solid of revolution into an infinite number of shells. A few moments ago when I calculated the volumes of the 8 shells, we got 56.0423. And here's the volume for an infinite number of shells. We can see that they're very, very close to each other. And that's the end of the video.